I'm Travis, and I'm going to talk about our adventures in ThreadperCore programming and async with Redpanda and Seastar, with a focus on coroutine performance. A bit about me: I love going deep into performance, all the way down to the assembly if necessary. Don't worry, there's not going to be a lot or even any assembly in this talk. I've held principal staff roles at Salesforce and architect roles at SAP and Business Objects. In the past, I had hobbies, including writing a blog about software performance. Then I became a parent, so those things are on hold for now. This talk isn't about Redpanda, but I'll give a quick overview because it motivates a lot of what we're going to talk about later. So Redpanda is a streaming engine, and it talks Apache Kafka. So clients talk the Kafka API to Redpanda to produce and consume message from topic partitions. We might have 10,000 or more partitions per cluster, and partitions are essentially logs stored on disk. Each partition is a raft group for consistency, usually with 3 members, so we use raft protocol for replication. And in general, we expect to be able to scale out Redpanda to many nodes or scale up Redpanda to larger nodes with many cores, and the behavior and performance should be equivalent. It shouldn't matter whether you decide to do scale up or scale out. So let's talk about ThreadperCore. ThreadperCore, well, like the name says, it's one thread on every core, and its thread is pinned to that core. Really, it withdraws the scheduling decisions from the kernel, and we have to make scheduling decisions in user space. The kernel scheduler is still running, of course, but it doesn't have anything to do because we've forced one thread to run on one core. An outcome of this is the thread must not block. If we make a blocking call, that thread won't be running on that core, and there's not going to be anything else to run instead, so we will be wasting that resource. So the question is, how do we replace blocking calls in this scenario? And the answer is Seastar. So Seastar was created by the fine folks at ScyllaDB, and really Redpanda is built on Seastar. So we have like a dozen third-party dependencies, but Seastar isn't just another dependency. Redpanda is built on top of it, and there's a synergetic relationship there, and we love Seastar. So what's Seastar? It's a framework for implementing a shared nothing service, and the service we made up of shards. A shard is one CPU core, an associated pool of memory dedicated to that core, and drawn from the NUMA local node for that core. And it's an all-to-all mesh of queues so that every shard can communicate with every other shard. So if 2 shards want to communicate, there'll be a dedicated single producer, single consumer queue where they can send messages in memory. And it implements cooperative multitasking. So a running task can't be suspended at any point except for known suspension points. So it really changes the way you write concurrent code because you don't have to worry about race conditions except at specific points where you know a task might be switched out. Now let's talk about async with coroutines. First, we won't talk actually about coroutines, but about the original Seastar style of async before coroutines were introduced. So on there we have a sample of code from Redpanda, cleaned up a bit, but showing what happens when we stop a raft group. So we have these various subservices within the raft group, like the event manager and the batcher, that we need to stop. Each of these stop events is an asynchronous invocation. It may not return right away. It may need to flush things to disk and return. So in general, we try to stop the first service, which is the event manager, and then we're attaching to the future that's returned there a continuation, which will stop this other service. And then again, we're attaching another continuation, which is stopping all of these services. So the first thing you might notice is like, this is mostly boilerplate and lambdas, and there's very little going on, but a lot of code, and it's pretty confusing. But this is the outcome of the continuation style. And lifetimes are also difficult to reason about in this scenario. So we're capturing this pointer to the local object, and normally you can freely use a local object within a method of that object, but here something external would need to ensure that the object is not destroyed before the final continuation runs, which may happen long after the stop method has returned itself. So what's going to come and save us from this kind of these dark ages? Well, C++ 20 introduces coroutines. We have the 3 new keywords, co-await, co-yield, and co-return. But it's not really a batteries included implementation. The language provides the concept and a lot of the wiring in the compiler, but you still need a framework to implement the promise type. The framework needs to schedule tasks that have been suspended. So at least half of the work is left to the framework. And in our case, the framework is Seastar. So Seastar defines the promise type and all the other associated stuff to make coroutines into a viable async programming model. So this is the same method written in the coroutine style. It's a lot clearer. In fact, it looks almost exactly how you would write it in blocking threaded model. You just call the stop methods one after another. The only difference is you write co-await in front of each of them. For example, this op block broken is not a synchronous method, async method, so you don't have to write it there. Internally, there's a deep transformation that's going on, breaking up this method into many possible suspend and resumption points. So there's a lot of magic you don't see, but definitely for the developer, it's a lot easier. So there's a side-by-side comparison. You can sort of see the new world on the left and the dark ages on the right. And I think almost everyone would agree the left is a lot nicer. So let's talk about performance. Not only about the performance of coroutines, but about async in general. Is this free? What kind of costs are we paying for this? So just like the implementation of coroutines is split between the framework and the compiler, performance is going to depend on both. So what I'm going to talk about here is Seastar's implementation and mostly Clang. So the numbers are from Clang 16, although they haven't changed much going back 3 or 4 versions. And of course, they are from Seastar. So you might, if you have a different promise or feature implementation, you might get different numbers, and the compiler may also make a difference. Though we have used GCC extensively in the past, and we haven't noticed a giant difference. The executive summary before we dig in is that no, coroutines are not a transparent drop-in when it comes to performance. So in many cases, they will be plenty fast, but when you dig down to leaf functions that need to be very fast, coroutines can have a large cost, and so can traditional continuation-based async as well. So the elephant in the room is coroutine frame allocations. This is a bit of a confusing topic because you hear a lot about possible optimizations that the compiler may make to optimize away allocations. And sometimes that gets sort of translated into, well, probably the compiler will optimize away the coroutine frame allocation, or just don't worry about it, the compiler will handle it for you. But our own observation is in our code base is that almost every coroutine invocation will allocate. It will allocate immediately when the function is invoked. It will allocate the coroutine frame. There are exceptions. So if the compiler can statically prove that the coroutine never suspends, I find that at least in Clang, it will elide the coroutine frame allocation. So that could be because there are no suspension points at all, the suspension points are never reachable, or that they are reachable, but they don't suspend. The problem is the compiler has to be able to statically prove that to apply the optimization. In Seastar specifically, the default is that you may suspend because the future is not available. So you wanted to read a byte, but the socket wasn't ready, didn't have your byte. So you suspend. But it may also suspend because your task has exhausted its task quota. So a task should run for a certain amount of time. When it reaches that quota, Seastar will suspend it at the next point. So because of that second possible suspension point, even if you're returning a ready future that the compiler can see and understand, the other reason for suspension will always be there, and generally the compiler won't be able to prove that it doesn't suspend and elide the allocation. So here's a concrete example. This is, I call it empty coro, should be almost empty coroutine, but it has one co-await call in there, and it returns make ready future. So make ready future is just immediately returning a ready future. It's an inline method that's visible to the compiler. So the compiler knows that the state of the future is ready. It's also inside a if statement that at runtime never executes. So not only does this routine never suspend because the future is always ready, it never even executes the co-await. So we never enter into that branch. The compiler can't prove that because this is a global variable that is mutable. But at runtime in the benchmark, it doesn't enter the branch. So how long does this take to do nothing, essentially? Well, it's 200 instructions and 80 cycles, and it always allocates once. Half of that cost, I sort of roughly bucketed it, looking at perf. Half of it is the allocation. That adds up to about 40 cycles, 100 instruction worth. And the other half is just the mechanics of setting up the frame, saving stuff in the frame, a lot of stuff. I'm not sure because there's no local variables or parameters, but there's a bunch of stuff. 104 bytes is the size of the frame. And that's where the cost comes. So this transformation to make this a coroutine is definitely not free. Let's take a more detailed look at a case study for a variable integer decode. This is drawn from Redpanda code. I cleaned it up because we tend to have these giant, sometimes method names that don't let things fit on the slide. But the coroutine method you're going to see is basically real Redpanda code. People are probably mostly familiar with what a variant is, but briefly, it's a variable length integer, 1 to 5 bytes, and the top bit of each byte indicates whether more bytes follow. So the last byte will have a 0 bit, and the decoding just basically consists of stripping out the top bit and smashing together the 7 payload bits into the final value. It's widely used in Kafka protocol. Almost every API uses it for lengths of structures and things like that. And it's also widely used elsewhere. I think Kafka uses the exact same variant as protobuf, for example. So here's an example of our Varant decode function. I'm not showing the decoder itself. That's inside the var decoder. That decoder class just accepts 1 byte at a time and does the work of accumulating the result and determining when the variant has finished. So in the loop, we basically read 1 byte from the input stream. The input stream might be backed by a file or connected to a network socket or just an in-memory buffer, but that's where the async call comes in. If we try to read a byte, but it hasn't arrived on the network yet, this call may suspend. So we read the character and then we pass it to the decoder. In fact, if you were to write this in a synchronous way, it would look almost exactly the same. Just the co-await would disappear and the return would be there instead of co-return. A key point is that the read method, which reads 1 character, could suspend, but it almost never suspends in practice, right? Like at least 1 packet is going to arrive once you've read the first byte, which probably happened earlier when you're reading the header or whatever. After that, you'll be able to read at least 1,000 bytes, usually much more, without suspending. So the chance of suspending is, let's say, less than 1 in 1,000 generally. So the behavior of the function and the performance when it doesn't suspend is extremely important. This is a coroutine, so following the rules that we mentioned earlier, it has 1 allocation per decode. So how fast is it? Well, to decode 5-byte variant, it takes 680 instructions, 220 cycles, 176 bytes allocated. So to me, that's a lot. Like just thinking of the operations to decode a variant, they're fairly simple. It's like strip out the top bit, shift the bits into place, order them together. Should be like 10 instructions per byte, maybe also some bookkeeping for the input stream. So I think this has large costs. Can we make it any better using a different approach? Let's continue the case study with a continuation-based decoder. So we go back to the dark ages. We try to use continuations because we know they don't allocate except when they actually suspend. That's the difference. They only allocate if the decision is taken to suspend. So it's more complicated. It's recursive method. We don't show everything here. There's actually this is the recursive method, but there's a setup method which needs to create the decoder and initiate the recursion. But basically, we read 1 byte from the stream, attach a continuation to that future that decodes the byte, and if more bytes are needed, it just calls itself recursively. So it's important to note that recursion is not a recommended looping idiom in Seastar. There are built-in looping idioms. The main problem with recursion is that you may have unbounded recursion or very large recursion. And Also because the stack frame sizes are often hard to predict, even a few hundred frames may cause a stack overflow. So here we are fine to use recursion because we know that we can make at most 4 recursive calls. We're only going to read 4 additional bytes after the first one. That's an invariant built into the decoder because of the way the variant works. So is it any faster? Well, here's a plot. We have the variant length on the x-axis, so from 1 to 5 bytes, and then the decode time in nanoseconds on the y-axis. So the answer is, it depends. For very short variants, the continuation is faster for 1 and 2 bytes. At 3, they cross over and they're equal. And for 4 and 5 bytes, the coroutine approach is faster. So this is just a direct outcome of what we mentioned earlier. To invoke the coroutine initially, we have to set up this frame, take the allocation, large initial cost, but then the decode loop will run in that coroutine context, reusing the same coroutine frame at a lower cost. In the continuation case, we sort of, it's like pay-as-you-go approach. We don't take any initial setup cost. We don't do an allocation. But every time we attach this continuation and call the recursive function, we need to copy the decoder state into the lambda, and then we need to copy it again to do the recursive call. Normally you would use move if possible. In this case, move and copy are equivalent because the decoder just has primitive values, but all of those things add up. And that's why as the variant gets longer, the continuation approach starts to lose. So we have mystery methods in there. What are these other 2 methods, this yellow line and the green line? Well, one is this optimistic approach. We already know that we usually are going to have the byte available when we read it. So we read the byte and we check if it's available. If it's available, we just send it right to the decoder and then try to read another byte. So this get method is only allowed to be called if the future is available. So essentially we do an optimistic loop that tries to stay totally in the synchronous domain. Note that there's no continuations here, there's no co-awaits. And then if that fails, we fall back to the recursive approach. So this doubles the amount of code, but it's twice as fast. It's twice as fast as the coroutine approach and follows the same trend. And it's also faster than the continuation-based approach. The other mystery method is just a synchronous version. So I just removed the co-await, removed the co-return, replaced it with return, and it forms a baseline. So you can see that it's much faster, 4 to 9x, but we can't really use it because in reality, the input stream read method can't be synchronous because it may sometimes block. But I've included it here as a point of comparison. So what should we really do? What is the compromise solution? Well, I think a reasonable thing is sync with async fallback, similar to the third method we saw, but we will extend our input stream to basically offer peak. So we'll say, can you give me 5 bytes and can you do it synchronously? If so, we will just pass those bytes directly to a decode method that will decode all of those 5 bytes at once, not with the loop and the passing to the decoder. And then we will increase the input stream. We will skip over the number of bytes that we consumed. So this is totally synchronous, and it also has the advantage of copying the buffer just once into the function and then decoding without further bookkeeping on the input stream. And then if that doesn't work, we just call our existing coroutine decode function. It's very key here. It has to be a separate function. So this coro decode, which is the coroutine decode method we saw earlier, if you were to just copy paste the code into this fallback method, it would turn this into a coroutine. Right now, it's not a coroutine. There's no co-await, there's no co-return. So you have to keep the method separate to prevent the coroutine transformation from happening. If the compiler inlines it, that's fine. It's not going to change this into a coroutine, I don't think. So what's the bottom line? Async is still cheap in the large. So we're talking about 200 cycles here and saying that's too slow. But context switches are thousands of cycles and have other knock-on impacts on the cache. So still generally going to be much faster than a threaded model. So just know that very short coroutines may be expensive. If you're calling coroutines very frequently and they're doing very little work, you might try to rewrite those leaf methods as continuations. On the flip side, continuations have a per continuation cost. If you have an async method that has a loop in it, consider coroutines because they pay this upfront cost, and then the looping is relatively efficient. Finally, in the most important cases, consider sync versus async fallback, and you should drive the above decisions via profiling. Not don't apply these by default. Apply them in your known hotspots. All right, that's my talk, and I love to talk about this stuff too. So if you have any questions, you can always reach out to me here on my contact information. I'm happy to talk about this stuff offline.